In this video, we're going to talk about Topic 9, Testing a Claim on Paired Data. So what we're going to find is that this test is a little bit different than the other tests that we've looked at, but it's actually going to be ran using the same test that we did when we were testing a claim on a single population mean with the population standard deviation unknown. So sometimes it is of interest to take a same measurement twice, either a before and after or other means of comparing two measures that are similar. So for that reason, it's also called a repeated measures test. And then I state down here that it's also called a dependent t-test. So an example of this would be weighing a person before and after a weight loss program, taking a blood pressure before or heart rate before and after exercise, measuring a vehicle's gas mileage on two different types of gasoline, and measuring a battery life with two different types of usage. So when this happens, when you have a repeated measure, so we'd be taking the weight on the same person before and after the weight loss program, the same person before and after the exercise, the same vehicle before with the first gasoline, and then the same vehicle with the second gasoline. So we do have a comparison that we're making, but it's going to be treated differently than the two population test. So one of the major indications of that is that for the two population mean test, one of our assumptions is that the means are sampled from independent samples. Well, this is clearly going to be violated with the paired test because it depends on that first measurement that's taken. So for that reason, all of the problems that we see with this are the same person before and after. This is the same stalk of corn before and after, but it doesn't always have to be a before and after. So this next example compares the front end vehicle cost on the same make and model vehicle. So front end repair cost, rear end repair cost. So comparing these two on the same exact type of vehicle makes this a repeated measure. So these two pairs depend on the fact that they come from the same exact vehicle. So this is the same person standing and then laying down their blood pressure. So this isn't a before and after, but it's still an individual. And then this last example is on the bone mass of women from post-weaning and during breastfeeding. So it doesn't have to necessarily be a before and after. The key here is that the two of them depend on each other. So this is different than the two population test because we don't actually care what these individual values are. We just care how they compare to each other. So the major assumption, the major thing that we're going to be testing with this is the mean difference. So we never are testing about two separate populations. They depend on each other, so they're really part of one population. So the major thing that we typically test with this is that there is no difference between the two groups. So if it was a weight loss program, then the people, didn't lose any weight while being on this specific diet. So we don't care about their starting and end weight, we just care the change that has happened while they were on the diet. So if we're testing for no difference, HO is going to be that the mean difference is equal to 0, and H1 is that the mean difference is not equal to 0. So this is that they're exactly the same, and this is that there's some kind of change, either positive or negative. However, there are lots of other things that we can test for this, and what we'll find is that the order of subtraction is extremely important. So I have a list of the different types of things that we could test on these. The first one is that group 1 is statistically greater than group 2. It's never going to be worded this way, but this is eventually what you will boil it down to when you've been given some kind of claim. So for the first one, group 1 being statistically greater than group 2 means that if we subtract in this order, group 1 coming first minus group 2, if this number is always larger than the second one, then it would statistically be positive. So that's what it means for the difference to always be greater than 0. So the other ones are pretty similar in nature, except for we eventually end up getting the difference being a certain number, But again, this is going to be the same thing as running a one population mean test. So this is actually going to be the same test when we get to running it as this column right here to the right. There is a way to put a paired test into Stata, but I actually don't run it like that because I think it takes away from understanding what you're actually doing. But if you're welcome to do that if you figure it out and find that it's the same. But we're going to need to find the differences every time anyway, so we might as well use them and treat this as the same exact hypothesis test as one that we've done before. So the other options is that if group 1 is statistically less than group 2, this is always going to be a smaller number than this, and statistically it would end up being a negative difference because this number is always smaller. So for example, 5 minus 9 would be a negative 4, so that's like what it means for the first number to be smaller. And then these are the same thing except for instead of having them just be greater than or less than, you can have them be greater than or less than by a specific number. So setting these up is, in general, the tricky part. And then once you've done that, it's really functioning very, very similarly to topic 3. So let's look at the reference tables. The assumptions are a little bit different, and neither of these assumptions, well, I guess this one is, if you didn't have this, you wouldn't run this test. But the second assumption, if it really doesn't matter if this is bad, it's a better case for this test. It makes it a little bit stronger if this assumption does pass. So if this fails, if you don't think that the differences are approximately normally distributed, you would just, say, not really and keep going. If this fails, it's really not a big deal to still run this test. The only time I would ever not use this test is if the data was really, really spread out and was, really kind of gross looking. But an important note that I want to make visually on this is that this doesn't say that the population is normally distributed, because it doesn't matter what the population is behaving like. We just want to have data that is normally distributed. So we are not going to use the Shapiro-Wilk test. So what we are going to be doing is a histogram only. And so this is really important because the Shapiro-Wilk is testing to see if the population, the data comes from a population that is normally distributed. And we only need to know that the data is decently well behaved. So this one is kind of funky, but the pairs, it's actually really complicated thinking about the pairs together. So it doesn't matter what kind of population they come from, so whatever your before and after are, because the differences, even if the populations are well behaved, the differences don't have to, match up in a way that the differences are normally distributed as well. So this should look exactly like the t-score. And then we're going to be running the t-test calculator, which is the same one that we had ran when we did topic 3. Our interpretation of our confidence interval is pretty similar, but let's look at one so we can see how exactly this is the same test as we've run before. So this first problem is part of the National Health and Nutrition Examination Survey. And the Department of Health and Human Services got the self-reported heights and the measured heights for males aged 12 to 16. So this is kind of an interesting problem because society can kind of pressure people into wanting to be a certain way or maybe be different than how they are. So this would be a good analysis of how these boys aged 12 to 16 are reporting their height compared to how they are. So will they tend to overestimate? Will they, tend to just say the height as they were when they were last measured? So when you put this into Stata, you're going to enter this in 2 columns. And then you can find the differences manually, although I don't recommend that. So what I would recommend doing is using, there's a change or create data option in the data editor, and we're going to create a new variable. And so I always name the new variable difference. But one thing that's very important is you need to specify somewhere on this paper what the order of your subtraction is. So in this first problem, it doesn't specify greater than or less than. It just says test a claim that there is no difference, which means that this is claiming that the reported height is statistically the same as the measured height that those boys reported for their heights to be. So we actually don't care what their heights were and what their guesses were. We just care how close they were to reporting their height accurately. So because of that, we don't need to specify a specific order. So I always just do, honestly, whichever one is higher most often, minus whichever one is lower most often, because I find it easier to deal with positive numbers. But sometimes you can just do the reported minus the measured. Either one would be okay. So we don't want to find these manually. What we can do is create an expression for this. And so you get two parts to a menu here, and we want to use the variables that we've entered in. So clicking on variables pulls up the two variables that we have in here, and then we want to do reported minus measured. And so when you hit OK, if you have nothing in here, it's not going to be happy. So when you hit OK, it gives you an error and it says the main tab variable must be filled in. So this is requiring you to name this variable, probably just in case you were making more variables, that you didn't have them all, var1, var2, you had them named so you know exactly what that variable is trying to say. So then when you hit OK, it gives you the differences. Sometimes they come up like this, and I would just honestly ignore it. So the difference between this one is 0.1, but for some reason it's coming up like this, and there's a way to fix it, but it's not going to make a difference in your answer. This is actually pretty common with a lot of statistical software, and I'm actually not completely sure why it does it. But so some of these came out nice, but other ones of these came out all funky. And I find this is just sometimes the way that the data is summarized. So let's see if total digits. No, that's worse. We don't want that. So yeah, when this happens, I usually just ignore it because it doesn't have an impact on the answer. So it's very unusual, but it happens with the other two software that I use as well. So I would just leave that. And so if this happens, you're just gonna leave it be, because it's off by so small of an amount. But it is very strange. But again, it will happen, and it happens in Excel as well. So this now is the column that we want to run our test on, and we're going to do just a one sample mean test. We're just going to make sure that the symbol we use is mu sub d. So for the setup of this problem, we're going to have the initial hypothesis as mu sub d is equal to 0, which is that they're statistically the same, and mu sub d is not equal to 0, which means that they're statistically different. So what I like to do is I always like to find the summary statistics. I think it's really important to do that because it gets you an idea of, okay, well, -1 is my mean difference. So I found the mean of that difference column, which we'll do right here. So -1 and a standard deviation of 3.519554. So it was off by that little teeny amount, but I mean, I didn't round this one just because I wanted to, if you wanted to use this in the actual hypothesis test, I would use it without rounding any of the values. But I would just let Stata use the column of differences that you have. So next, checking the assumption. Matched pairs is going to be kind of a way to guide you into the fact that this is the test that you're using on the differences instead of the difference in the mean. And the test probably would have a different result for, I'd say, about half of the problems. So sometimes if you kind of are using the two population tests instead, you may end up with the same result, but it fails that independence assumption in a way that it wouldn't make sense to use that test. So differences are approximately normal. The way that we're going to check this is just making a regular histogram. Histograms, again, are a little bit risky of a graph because if you change your bottom axis, your graph shape can change completely. So our data is continuous. We are going to make a histogram of the difference, and I just let it make whatever its default histogram is. So I actually made this in Stata at another time, and so this has ended up being a completely different looking graph. So if you want to, mess around with your histogram, what you would do is change the bins, and the bins is the same thing as the class width. So that's usually what software calls the bins, or the class width. So let's have it do 5. So this now is a very different looking histogram. So I failed this because I didn't think that it looked bell-shaped. However, again, if this, unless it's like really far spread out, maybe from 0 to 100, and it's, every maybe around 10 values do we get a little bar. I don't know. I would still always use this test unless it was really, really bad. So when we run this test, we're going to be doing the same thing as the one sample mean test, but we're just going to be running it on the differences. So the test that we'll select is the t-test mean comparison test. So a calculator we're going to use if we want to just put in these summary statistics here, but I don't want to round it all. The mean comparison test is going to be just a regular one sample. If you want to, you can put in paired and indicate your 2 variables. So I'm going to show how that is the same thing, but I don't think it has as good of an understanding of what's happening than just running a regular one sample test. And we already have the differences, which is the, the kind of the new part for this. So we're testing for a difference of 0 and our confidence level, so we're two-tailed, so it will be 95% if we're at the 0.05 level. So even though it was rounding kind of funky, we still ended up with the same t-score and p-value. So those two should never be affected by this. I mean, this is 6 decimal places. It's different by. So again, I know it's really weird, but every single software I've ever used does that. So the t-score is negative 0.98, which is pretty close to the middle of our distribution. It is a two-tailed test. So that negative 0.98, which falls pretty close, is going to end up being doubled. So we have 2 tails on both sides. And the total p-value together of both shaded areas is 0.3461. So the p-value is high, so the no will fly. So that means that we're going to fail to reject HO, and we're going to support our claim because HO is our claim. So then our confidence interval has negative 3.24 to 1.24. And so since 0 is inside this confidence interval because there's a sign change, so it goes from negative to positive. So that means on a number line, if we plotted these, we would have 0 in the middle. This supports failing to reject HO. So again, notice that I do have on this page somewhere the order of my differences. So the fact that this is more negative means that they were actually underreporting in general. However, they didn't underreport by enough that the difference was statistically different from 0. So 0 is inside, so this supports failing to reject HO. So I'm going to go through one more. I did include extra practice problems on this one because setting it up is the challenge, and it comes with experience that you can set them up with confidence. So the next one that I'm going to look at is the second problem, and a farmer decides to try out a new fertilizer on a plot of land that contains 10 stalks of corn. Before applying the fertilizer, he measures the height of each stalk. 2 weeks later, he measures the stalks again, making sure to match each stalk's new height to its previous one. So this after height is very important. It depends on the previous height. We don't really care what these initial stalk heights are. We only care how they've changed from one to the next. So the stalks would have grown an average of 6 inches. So in order for this fertilizer to be effective, they would need to have grown more than 6 inches. So in order to determine if the fertilizer helped, then the difference needs to be greater than 6 inches. So with the setup of this next problem, we're testing to see if the mean difference is equal to 6 or if the mean difference is greater than 6. So let me open this one. So when you open a file, just as a reminder, the data is here. It just doesn't appear unless you specifically ask for the data editor to show up. So with the data editor here, we would need to set up a new variable. So we're going to create or change data and then create a new variable. So this variable that we're creating, I'm again going to call this difference. And now the order that we want this subtraction to happen is we want to have it be the after height minus the before height. So when we create this variable, it's going to be after minus before. So this is really important because if we did it the other way around, the difference would be more than -6, or actually less than -6, and that really doesn't make sense to us because we want to see that, okay, that it's grown 6 inches. We would never say that, you know, the before height was 6 inches less. So we could say that, but it would be kind of weird to say. So when we hit OK, these appear, and again, it's doing this. This always happens after I open the file from a saved data file. So we're going to leave this. It's not going to be a big enough difference to affect our values. And so again, I would find the summary statistics just to get an idea of you know, how close is it to 6? Are we expecting there to be a change? So getting the regular summary statistics, we're getting 7.36 and a standard deviation of 2.05329. So this standard deviation didn't end up being different. The low and high ones were different enough that they, or even enough that they cancel each other out. So next I would check out this histogram. So let's open another version of Stata. We don't need that. So the histogram is again on continuous data. So remember, discrete is if it's just like number of people, or you know, something that can't be broken down further than whole numbers, or something with maybe 1 decimal place, because otherwise if it has decimal places I would put it into this as continuous, just because of the graph, the way that it gets set up. So if we set this up for 10 bins, there's only 10 numbers, so this is going to end up being a pretty odd looking graph. But if we've changed this honestly isn't too bad looking. So it's not perfect, but it's definitely not so horrible that I would feel that it's, I don't know. This is pretty, doesn't really care about this assumption very much. So it does go up and down a little bit, but again, I don't really think this is too bad. What I will notice is that some of them are less than 6. So we have some that are in the 6 bin, and then, you know, more of them are higher than 6, but there are a couple that are less than 6 as well. So I don't know if this is a big enough difference to pass this. And not only that, it's up to the farmer to determine, well, you know, maybe it's really expensive to apply this fertilizer, or maybe it's, you know, going to end up damaging the soil or something like that. So it's not just up to the statistical result to determine if this should be used. It's always a full, you know, thought. So when we run this test, we're going to be, again, running the same t-test that we did at topic 3, except for we're going to always be using the test and not the calculator, because we will have the data given to us for this. So now we want to show how this compares to 6, not 0. And so then, are we 0.05? Yep, so this would be a 90% confidence interval since we are one-tailed. So when this gets ran, we end up getting a t-score of 2.09 and a p-value of 0.0328. So this p-value is less than 0.05, although it is close to that cutoff, but we've set it first in advance for a reason. So it's low compared to 0.05, so we reject HO, which means we support our claim. Then we have our t-score up here on the right end and our p-value in our shaded area. So the confidence interval from Stata is 6.17 to 8.55. Since 6 is not inside the confidence interval, this supports rejecting HO. And then the minimum difference is 0.17 inches, and then that goes up to a maximum difference of 2.55 inches more. So maybe this is, you know, a big enough difference, but maybe they find that it's not high enough compared to 6 in order to be worth the expense and the extra work that it causes. So like I said, there is extra practice in this topic because setting them up is the most important part. Usually once that happens, people kind of fall into their routine with the 7 steps, especially since it's a test that we've already ran. So the answers to all of these are posted, and the data for a few of them will be in the folder. So if you have any questions, please feel free to send me an email.